Welcome to the second half of section 8.1. In the last lesson, we talked about solving a system of equations through graphing and substitution. In this lesson today, we're going to talk about the elimination, sometimes called the addition method, and then some application problems. So let's start with the elimination method steps. Just like substitution, I went ahead and put them on the slides here for you for the first couple, in case you need a little refresher from Algebra 2 for those. The first step when you're solving using elimination is you want to adjust the coefficients by multiplying through a number so that the coefficients of the same variable are opposites. Notice in the equation we're given here, all of my variables are lined up. The x's, the y's, the equal signs, the numbers on the other side, the constants, but there's no easy variable to get alone. So what we do is we add or subtract by elimination to get rid of one of our variables. And this first step is explaining how we do that. If you have variables that do not have opposite coefficients, like a 3 and a -3 or a 5 and a -5, you multiply one or both of the equations by a number, and we're going to try to stick with integers on this to get them to be opposites. At that point, you can move on to step 2. You're going to add the equations together, or if your variables happen to be exactly the same, you could subtract as well. Once you do that, it'll drop out one of your variables and you'll be left with one variable, so you have a one-step equation you can solve. That'll give you your first answer, either your x or your y. You can then plug that back in, like we did with substitution, into one of the original equations to get the other part of your answer. And then again, just like substitution, we're going to check it the same way. We're going to plug our numbers back in for our x's and our y's and make sure they work in both equations. So let's go ahead and get started on the first problem. Our first equation, 3x plus 2y equals 3. Our second equation, 9x minus 4y equals 4. Like I mentioned earlier, everything here is lined up, but we have no opposite coefficients for either our x's or our y's. So we're going to have to multiply by something. Let's say I choose to multiply the top equation by a number, and you could really multiply either one. We need to make either that 3 look like a -9, or the 2 look like a 4. Now it's probably going to be easier to make the 2 look like a 4 only because I can multiply through a positive instead of a negative, and I'm less likely to make a mistake there. But again, if you chose to multiply the 3x by a -3, that would work here as well. So you are going to have some amount of choice in this problem like you did with substitution. You just need to make sure that you distribute that number through the entire equation, so I always use parentheses when I do this. 3x times 2 gives me a 6x, 2y times 2 gives me a 4y, and then 3 times 2 is going to give me a 6. Now you can take these two equations and add them together. 9x and 6x, we're just adding down our columns, gives me 15x. My y's are going to cancel out, and that's what should happen every time if you're doing elimination right. If your variables don't cancel out, you want to go back and multiply by something different, or check your work. 4 and 6, add those together, I get 10. Divide by 15. I'm going to get x equals 10 over 15, which reduces to the exact fraction 2/3. So that's the first half of my answer. Now, like substitution, we're going to plug that back into either of the original equations. Let's say I use the top equation. X is 2/3. Plug it in. 3 times 2/3 just gives me a 2 because those 3's cancel. Think of it like a 3 over 1. We're multiplying numerators together and denominators together. Plus 2y equals 3. Subtract 2 over. 3 minus 2 gives me 1. And then divide by 2. I get y is a half, or you could use 0.5 for that one. So our final answer, 2/3, 1/2, which again you can check by plugging it in, or you could look for that intersection in the calculator. It's a little bit harder in the calculator because the y isn't isolated for both of these. If you're doing it at home, you could even look at Desmos. Potentially would be an easy way to plug it back in and check. All right, let's try one more of these together. First equation here is 3x minus 2y equals 1. Second equation, -7x plus 3y equals 1. So again, I need to make my x's or my y's look like one another but be opposite, one positive, one negative. The good news is they're already one positive, one negative in each pair of the x's and y's, but my numbers don't match. And I can't multiply a 3 by an integer to get a 7 or a 2 by an integer to get a 3. So what we do in this case, so we don't have to end up with messy fractions and decimals, is just multiply both equations by something. Again, you're just trying to get opposites, so there's a lot of different choices here. My route that I use is I just take two coefficients that are in front of the same variable and switch them, like the 3 and the 7. If I multiply the top by 7 and the bottom by 3, they'll both be a 21, one positive, one negative. Or if you wanted to stick with the y's, you could multiply the top by 3 and the bottom by 2. And then just remember, you may need to throw a negative in there to make sure they're opposite. Distribute the 7 through the top. 21x minus 14y equals 7. Distribute the 3 through the bottom. All right, distribute the 3 through the bottom equation. I have negative 21x, positive 9y, and 3. Add my equations together. X's will cancel, negative 5y and a 10. Divide by negative 5, we're going to get y is negative 2. Plug that back into either original equation. Let's say I use the top one, 3x minus 2 times negative 2 equals 1. 3x plus 4 equals 1. Subtract the 4, negative 3, x is negative 1. Final solution, negative 1, negative 2. So what happens if we have fractions in a problem? Let's look at this one. I have x over 2 plus y over 3 equals 1, and 3x over 4 plus y over 2 equals 1. So everything's lined up. I probably don't want to use substitution because, again, not very easy to get a variable isolated, but I definitely don't want to deal with these fractions if I can avoid it. So an optional, I can get this up here, there we go. An optional step at the beginning is you can clear fractions as long as, sorry that's not writing very well there, clear the fractions as long as you don't have any variables in the denominator like this problem. So you can see I just have numbers in my denominators. To clear the fractions, again, optional first step, is you multiply each equation by its least common denominator. So that top equation, if I have a 2 and a 3, the least common denominator is 6, because 6 is the smallest number that 2 and 3 both divide evenly into. Same thing with the bottom equation. Least common denominator is going to be a 4 there, because that's the smallest number that 4 and 2 both divide evenly into. Now we distribute it in to all three parts of our equations. Keep in mind, when we're multiplying these, think of it like a 6 over 1. There we go. And a 4 over 1. So we're multiplying 6 by the numerator and 1 by the denominator. That's going to look like a 6x over 2, which reduces to 3x. The second term will look like a 6y over 3, which is going to be a 2y. And then 6 times 1 gives me 6. And you can see I've cleared the fractions. Bottom equation, same thing. I'll have a 12x on top divided by 4, which is going to give me a 3x. I'll have a 4y on top divided by 2, which is going to give me a 2y. And on the bottom, I'm going to have a 4. Now, I don't have opposites, but I do have the exact same value. So this is an opportunity, instead of adding the equations, you can just go ahead and subtract them to get a variable to cancel. X's will cancel, and actually the y's will cancel in this problem as well. So we're left with 0, nothing on the other side. 6 and 4, subtract those, I'm going to get 2. And you can see this is something that we saw in the last lesson with substitution. If all of our variables disappear and we're left with 2 numbers, this is one of our special cases where it's either no solution or infinitely many solutions. If you have a false statement, the answer is no solution. And if you wanted to check it, you could graph both of these lines and see that they are parallel to one another, or you could calculate the slope of both of the lines. This problem also contains fractions, but we encounter a little bit of an issue now because I can't clear the fractions because my variables are in the denominator. So we're going to use a special substitution, let's call it a trick, for this one to make the problem an easier version of what we see. We're going to let u, and I'm just choosing that because that's what our book uses, but you can pick any letter you want, equal 1 over x. And we're going to let v equal 1 over y. Now, where are those coming from? If I think of 4 over x, that's the same thing as 4 times 1 over x. So instead of 4 over x, I can replace that with 4 times 1 over x, or just 4u. 3 over y is the same as 3 times 1 over y. So that's the same as 3v, and then just keep my 1. Do the same thing for the bottom equation. 2 over x is the same as 2 times 1 over x, so 2u. 6 over y is the same as 6 times 1 over y, so I'm going to have a minus. 6v equals 3. And now you can see this looks a little more familiar to us, like what we were doing with the other elimination problems. So let's go ahead and solve for u and v, and then we'll get back to x and y at the end. I'm going to multiply, it looks like maybe the top by 2 would work. So I'll have an 8u, a 6v, and a 2. And now I can add my equations together. 10u, v's cancel, and I get a 5. So u is 5 over 10, which reduces to 1/2. Let's plug that back into maybe the top equation. 4 times 1/2 plus 3v equals 1. 4 times 1/2 is 2. Subtract 2, I get -1. So v is -1/3. Now, our problem wasn't asking for u and v. We were asked to solve for x and y. So to do that, we're going to go back to our substitution piece. If u is equal to 1 over x, then I can replace u with 1 over x. And now I have 1 over x is 1 over 2. And hopefully at this point you can see the missing number. You can see if x is 2, I will have a true statement. If you're not sure about that, or if you have some weird numbers here, you could always cross multiply to solve because you have a proportion there. You can do the same thing for v. Because v is 1 over y, I can replace it. And you can see that if I make y equal to -3, I will have a true statement. Or again, cross multiply to solve. Final answer is 2, -3. You can plug it back in to check in the original problem. Okay, this problem is yours to try on your own, and then I'll show you the solution after you answer the question in Edpuzzle. Make sure, if you're doing this on a test or a quiz, you're writing out this piece. You cannot mathematically introduce new variables to a problem without defining them. So we're defining what u and v represent. So when you substitute in u and v, your problem should have looked like this. And this one was a little bit easier. You can see my v's are already opposite. If I add them together, 9u equals 6, and hopefully you left this as an exact fraction, no decimals, 2/3. Plug that back into the top. 3 times 2/3 plus 1v, so plus v, equals 4. 2 plus v equals 4, so v equals 2. To solve for x and y, substitute back in the 1 over x and the 1 over y. These ones maybe are not as obvious, so I'll show the cross multiplication steps to solve. If I multiply 1 times 3, I get 3. If I multiply 2 times x, I get 2x. So x is 3/2, or if you said 1.5, that's fine. Think of this like a 2 over 1. If I cross multiply, 1 times 1 gives me 1. Y times 2 gives me 2y. So y is 1/2. Final answer here, 3/2 and 1/2. Our last three problems in this lesson are word problems. We will not be, as part of the lesson, solving these. We're just going to practice setting them up. When you do solve them on your homework, you can use any of the methods that we've discussed already in this lesson. Solved by graphing, solved by substitution, solved by elimination. Personal preference, if it's me, if there is not a variable alone, I would probably use elimination every time. I think it's the simpler of all the methods and definitely more accurate than graphing. But again, you're going to have a preference there when you're doing it on your own. All right, let's go ahead and look at the first one. The sum of the diameters of the largest and smallest pizzas sold at Monster Pizza Shop is 29 inches. The difference in their diameters is 13 inches. Find the diameters of the largest and smallest pizzas. When you're solving a system of equations, you first want to define your variables. Your variables are whatever you're looking for. And usually that's going to show up at the very end of the problem. We see that a lot with math problems. So you can see here it says find the diameters of the largest and the smallest. And you can always use an x and a y if you like. I would recommend using variables that are going to make it easy to distinguish what each variable represents. For example, if I used an x and a y, it may be hard at the end to remember what did x stand for, what did y stand for when I want to label my answer. So I'll use L for largest, S for smallest. That way I don't get mixed up between the two. If you have two variables, which you should have a minimum of two variables for a system of equations, that means you need to write two equations. Both equations should contain both variables. So let's run through our sentences. The sum of the diameters of the largest and smallest pizzas sold at Monster Pizza Shop is 29 inches. Sum is a fancy way of saying adding. There's our first equation. Difference, the difference in the diameters is 13 inches. Now, addition, it doesn't matter how I add them up. S plus L and L plus S are exactly the same thing. But when we subtract and when we divide, order matters. So now we have to think about difference is subtraction for sure. We know that's going to happen. Do I do largest minus smallest or smallest minus largest? Hopefully, your brain is screaming, it's got to be largest minus smallest, because if I did smallest minus largest, I would have a negative number on the other side of the equation. And that's our system. From here, you can solve it how you like. If I were to recommend a way to solve this one, I would say use elimination, because you already have all your variables lined up and the S's are opposite. You could go ahead and very quickly add these together. Your S's would cancel out, find your largest one first, and then plug that back in to get the smallest size. I would like you to try this on your own. Take a minute, answer the question in Edpuzzle, and then when you're all done, I'll explain where these equations are coming from. Okay, so hopefully you have variables for doubloons and strings of beads. I'm going to use D for doubloons and B for strings of beads. There are two totals that show up in this problem, and hopefully that's what you have your equations equal to. The first total is how much he paid for everything. So I'll put a little money sign by that equation, $265. And the second total is how many items he had. So that's helpful to know because that can help you sort through the remainder of the information. It says at the top, he paid 40 cents for a string of beads and 30 cents for each doubloon. So the dollar equation will probably be where that information is going to go because we're talking about cost per item. 40 cents, make sure you have either a 0.4 or a 0.40 there. And that was for each string of beads, plus 30 cents for each doubloon was 265 total. Now the other total, there were 770 beads and doubloons, and that's just items. So that's B plus D. And then you can use those equations to solve. If I were going to recommend a way to solve this, I would again probably use elimination. I don't like decimals in my problems though, so just like our fraction problems, you can clear decimals by multiplying by an integer. If you have one decimal place, you multiply by 10. Like this problem, 2 decimal places 100, 3 decimal places 1,000, etc., etc. Now it's going to make the numbers a little bit bigger, but you won't have any decimals to work with. And then you could maybe multiply the bottom by, let's see, if I multiply the top by 10, I would have a 4 in front of the b. So I can maybe multiply the bottom by a -4, and then I could from there get my variables to cancel. Last one, again, try this one on your own. Let's read through it. A student earns twice as much per hour tutoring than working at McDonald's. If her average wage is $11.25 per hour, how much does she make at each job? So each job is what we're trying to figure out her wage for. Her two jobs are tutoring, let's use a T, and working at McDonald's, let's use an M. She earns an average wage of $11.25 per hour. I'm going to start with that piece of information. When we average, we add up two or more things and divide by how many there are. So I'm going to add up her wages, divide by 2 because of her two jobs, and I get $11.25. Now, if you want to make that equation a little bit easier, you could now multiply both sides by 2. So again, let's call this an optional step. If I multiply on the left by 2 because it's one large fraction, my 2's are just going to cancel, and I'll have m plus t that remains. On the other side, if you do 2 times 11.25, you're going to get 22.50 or 22.5. So that's my first equation that I'll use. The other piece of information you were given is that she earns twice as much per hour tutoring than working at McDonald's. One common mistake in this problem is because the way this is worded, students will say 2t equals m, which means if I'm going to read it out, 2 times her tutoring wage is her McDonald's wage. But that doesn't make sense because we know she makes more money tutoring. So instead, we say 2 times her McDonald's wage equals her tutoring wage. Therefore, her tutoring is twice her wage at McDonald's. And that is your second equation. This is a problem that I would probably use substitution for. At this point, your t is alone, so you could circle what it's equal to, plug that into t in the other equation, and solve from there. That's the end of our 8-1 lesson. Your MathXL assignment is due on the 7th at 11:59 p.m. Remember to post your questions in the Google Doc provided if you would like them discussed during our Google Meet sessions in class. Thanks, guys.